Imagine a star so massive, so powerful, ripped from the heart of its own galaxy and hurled into the void at speeds that defy the laws of physics. Picture it streaking across the cosmos like a runaway bullet, faster than anything should ever move, leaving behind a trail of shattered expectations and unanswered questions. This isn't science fiction. This is the reality of hypervelocity stars, celestial rebels that refuse to play by the rules. And what's even more astonishing, we don't fully understand why they exist. These cosmic speed demons travel at millions of miles per hour, so fast they could cross the distance from Earth to the Moon in mere minutes. Some are flung from the center of galaxies by the gravitational wrath of supermassive black holes, while others seem to have no explanation at all, no visible force powerful enough to launch them on such insane trajectories. They shouldn't exist, and yet here they are, tearing through the universe like ghostly phantoms, challenging everything we thought we knew about how stars behave. In this video, we're diving deep into 25 of the most baffling, mind-bending mysteries surrounding hypervelocity stars, from their impossible origins to the way they interact or refuse to interact with the galaxies they pass through. Each one of these behaviors leaves astronomers scratching their heads. Some of these stars even vanish without a trace, as if the universe itself is playing a cosmic game of hide and seek. So buckle up, because we're about to embark on a journey through the strangest, most enigmatic phenomena in the cosmos, where the rules are broken and the stars themselves are the ultimate outliers. One of the most jaw-dropping behaviors of hypervelocity stars is how some of them seem to be violently kicked out from the very core of their home galaxies, like cosmic outcasts banished by invisible forces. The leading theory: these stars get too close to the monstrous supermassive black holes lurking at galactic centers, where gravity is so intense it can fling them away at unimaginable speeds. Picture this: a star wanders near the black hole's edge, trapped in a deadly dance, until the tidal forces of gravity slingshot it outward like a stone from a sling. But here's what's wild: the energy required to eject a star this fast shouldn't just come from gravity alone. There's something else at play, some hidden physics we haven't quite cracked. Take S5HV-S1 for example. This star is racing through space at a staggering 6 million kilometers per hour, so fast it could cross the distance between New York and Los Angeles in under 2 seconds. Astronomers traced its path back to the heart of the Milky Way, where our own supermassive black hole, Sagittarius A star, likely hurled it outward. Yet even this explanation leaves gaps. The forces needed to accelerate a star to such extreme velocities defy our current understanding of black hole mechanics. Some scientists speculate these stars might have been part of binary systems, where one star gets captured by the black hole while the other is catapulted away in a gravitational slingshot. But that still doesn't account for all the energy we're seeing. And then there's the mystery of why only certain stars get ejected. Not every star that drifts near a black hole becomes a hypervelocity runaway. So what separates the ones that stay from the ones that flee? The more we study them, the more these stellar speedsters challenge our assumptions about how galaxies evolve, how black holes behave, and even how the universe itself orchestrates the motions of its most massive objects. Every hypervelocity star we discover is like a clue in a cosmic detective story, one that might rewrite the rules of astrophysics as we know them. But here's where things get even stranger. Not all hypervelocity stars follow the neat, predictable escape routes we'd expect. Some veer off at bizarre angles, loop around in ways that make no sense, or even seem to slow down before accelerating again, as if something invisible is tugging at them from the darkness. These erratic paths suggest forces beyond our current understanding, possibly hidden players in the cosmic game of gravity. Take the case of HVS3, a star that should have been racing straight out of the Milky Way after its explosive ejection. Instead, it took a sharp turn, almost as if it had hit an unseen wall. Astronomers initially chalked it up to a chance encounter with another massive object, but here's the twist: there was nothing there. No star cluster, no gas cloud, not even a stray planet dense enough to alter its course. This has led to wild theories, including the possibility of dark matter clumps, invisible, heavy patches of the universe's most elusive substance, acting like cosmic speed bumps. Then there's LMOST HVS2, a star that did the exact opposite of what physics predicted. Instead of slowing down as it traveled further from the galaxy's center, it suddenly accelerated, as if given an extra kick by something we couldn't see. Some researchers speculate this could be evidence of rogue black holes, lonely, drifting remnants of galactic collisions exerting their gravity without warning. But without direct detection, these ideas remain in the realm of educated guesses. The more we track these wayward stars, the more their paths seem to taunt us with unanswered questions. Advanced sky surveys like Gaia have mapped millions of stellar motions, yet hypervelocity stars continue to break the rules. Could they be interacting with structures we haven't discovered yet? Or are we witnessing entirely new physics where gravity doesn't behave the way Einstein predicted over vast distances? Every unexpected trajectory is a breadcrumb leading us deeper into the cosmic unknown. Some hypervelocity stars carry a secret in their chemical fingerprints, traces of a violent past where they weren't alone. These stars once belonged to binary systems, locked in a tight orbital dance with a companion, until a catastrophic encounter with a supermassive black hole tore them apart. The physics behind this cosmic divorce is both brutal and precise. When a binary pair drifts too close to a black hole, the immense tidal forces can rip the stars away from each other. One gets captured, doomed to spiral inward, while the other is flung away at mind-bending speeds. But here's what baffles astronomers. Some of these ejected stars carry abnormally high levels of heavy elements, a trait known as high metallicity, which shouldn't survive such a chaotic ejection. Take the star HE04375439, for instance. It's racing through the galaxy at over 2 million miles per hour, yet its atmosphere is littered with elements like iron and silicon, materials typically forged in the cores of massive stars or violent supernova. Conventional models suggest such elements should have been stripped away during the star's explosive escape, yet there they are, defying expectations. One theory proposes these stars might have been part of unusually tight binary systems, where their companions were already enriching them with heavy elements through stellar winds or mass transfer before the black hole intervened. But that raises another puzzle. How did these delicate chemical signatures survive the gravitational chaos of being hurled across the galaxy? The survival of these high metallicity stars suggests there's a gap in our understanding of how binary systems interact with black holes. Current simulations struggle to replicate the precise conditions needed to both eject a star at hypervelocity and preserve its unusual composition. Some researchers speculate that certain binary configurations might act like a shield, where one star absorbs the brunt of the black hole's disruptive forces while the other gets flung away relatively unscathed. Others wonder if these stars might have been part of triple systems, adding another layer of complexity to their violent origins. What's clear is that each of these cosmic fugitives tells a story we're only beginning to decode. Their existence forces us to rethink not just how stars escape their galaxies, but how they evolve under extreme conditions. If a star can be ripped from its partner, catapulted across the universe, and still cling to the chemical remnants of its past, what else might we be missing about the hidden lives of these celestial speedsters? Every new discovery pushes the boundaries of stellar physics, revealing a universe far more dynamic and far more unpredictable than we ever imagined. One of the most perplexing riddles about hypervelocity stars comes when we measure their age, only to realize many of them appear impossibly young. These stellar fugitives often show signs of youthfulness that contradict the ancient regions they were ejected from, like finding a toddler running through a retirement home. Take the star known as LS1 as an example. Ejected from the Milky Way's core, a neighborhood packed with elderly stars, it burns hotter and brighter than it should, with a chemical composition that suggests it's billions of years younger than its surroundings. The question isn't just how it got flung into space, it's how it managed to cheat time itself. The leading explanation involves a cosmic fountain of youth, stellar collisions or accretion, events that rejuvenate stars mid-flight. Imagine two stars grazing each other in a high-speed encounter, their outer layers mixing violently like paint in a blender, triggering fresh nuclear reactions and essentially reset the star's clock. Another possibility is that some hypervelocity stars strip gas from interstellar clouds as they barrel through space, fueling new bursts of fusion that make them appear younger. But here's where the math falls short. The energy required for such dramatic rejuvenation should leave visible scars, distorted shapes, unusual rotation speeds, or telltale debris trails. Yet many of these stars show none of these signs. They look pristine, as if they were born yesterday. Even stranger are hypervelocity stars like HVS 17, which not only appear youthful but also emit X-rays, a trait usually seen in stars with strong magnetic activity or close binary partners. Yet when astronomers scanned its surroundings, they found no companion, no recent collision remnants, nothing to explain its vibrant energy output. Some theorists speculate these stars might be tapping into hidden reservoirs of dark matter or interacting with exotic particles as they travel, though these ideas remain firmly in speculation territory. The deeper we dig into this mystery, the clearer it becomes that our current models of stellar evolution are missing a crucial piece. If stars can shed billions of years through processes we don't yet understand, what else might we be getting wrong about how stars live, die, and sometimes outrun time itself? Each of these cosmic anomalies forces us to rethink not just hypervelocity stars, but the very nature of aging in the universe. While most hypervelocity stars are thought to originate from our own galaxy's chaotic center, a handful defy even that explanation because they weren't born here at all. These intergalactic interlopers are cosmic immigrants, stars that somehow cross the vast emptiness between galaxies only to end up hurtling through the Milky Way at speeds that should be impossible. One such visitor is HVS 24, a star moving so fast it couldn't have been accelerated by any known force within our galaxy. When astronomers traced its path backward, they realized it came from the Large Magellanic Cloud, a neighboring dwarf galaxy over 160,000 light-years away. The question isn't just how it got here, it's what kind of cosmic slingshot could have launched it across that impossible distance. The most plausible explanation involves a scenario straight out of a gravitational thriller. Picture two galaxies passing close enough for their tidal forces to rip stars loose, like apples shaken from a tree. But for a star to gain enough energy to not only escape its home galaxy but also penetrate another, something far more violent must have happened. Some theorize these stars were ejected by supermassive black holes in their original galaxies, only to get an extra speed boost from the Milky Way's own gravity as they fell toward us. Others suggest they might be survivors of ancient galactic collisions, where entire clusters of stars were sent careening into the void during catastrophic mergers. Then there's the enigma of their survival. The space between galaxies isn't just empty, it's a wasteland of extreme cold and near-total darkness, where stray gas clouds and dark matter lurk. For a star to traverse that gulf without being slowed down or torn apart hints at forces we've yet to map. Take HVS 32, a star with a bizarrely high concentration of lithium in its atmosphere, an element usually destroyed in stellar cores. Its chemical fingerprint suggests it spent millions of years shielded somehow, possibly by a cocoon of dense gas or magnetic fields as it journeyed between galaxies. What's truly startling is what these intergalactic runaways reveal about the cosmos. Their existence implies that galaxies aren't just island universes, but are constantly exchanging material like trees in a forest sharing seeds. If stars can leap across millions of light years, could planets, or even the building blocks of life, make similar journeys? And if so, how many more of these hypervelocity travelers are out there, unnoticed, weaving an invisible web between galaxies? Each discovery forces us to rethink not just the life cycle of stars, but the very interconnectedness of the universe itself. Astronomers have a problem, a cosmic case of missing stars. Simulations predict our galaxy should be teeming with hypervelocity stars, flung outward by the supermassive black hole at the Milky Way's heart. Yet when we look up, we find only a fraction of the expected number. It's like throwing a handful of marbles into the air and watching half of them vanish before they hit the ground. So where are all these runaway stars hiding? One glaring possibility is that our telescopes simply can't see them. Hypervelocity stars ejected toward the outer reaches of the galaxy often fade into the darkness, their light too faint to detect against the vast backdrop of space. Others might be obscured by dense clouds of interstellar dust, their glow smothered before it reaches us. Even cutting-edge observatories like Gaia, which maps stellar motions with unprecedented precision, struggle to track the fastest of these stars once they've crossed a certain distance. Think of it like trying to spot a single flashlight beam in a foggy forest. The farther it gets, the harder it is to see. But the mystery runs deeper than just observational gaps. The ejection models themselves might be flawed. Current simulations assume hypervelocity stars are launched primarily through black hole interactions, but what if other forces are at play? Some researchers suggest rare cosmic events like the explosive disruption of a star cluster or the sudden collapse of a binary system could fling stars outward without involving a black hole at all. These alternative scenarios would produce fewer hypervelocity stars overall, potentially explaining the shortage. Then there's the wild card. What if some of these stars aren't missing but masquerading as something else? A few hypervelocity stars might slow down over time, their trajectories altered by encounters with gas clouds or dark matter. Others could be mistaken for ordinary high-velocity stars if their origins aren't traced carefully. Take the curious case of LMOST-HVS5, initially dismissed as a typical runaway until its path revealed it had been ejected from the galactic center at speeds only a black hole could muster. The gap between prediction and reality forces astronomers to confront uncomfortable questions. Are we overestimating the efficiency of black hole ejections? Underestimating the drag of interstellar material? Or is there an entirely new class of hypervelocity stars, ones that move so fast they've already left the galaxy entirely, vanishing into the intergalactic void before we could spot them? Every missing star is a clue, hinting that the universe's rulebook might need more than a few revisions. Some hypervelocity stars don't just break speed records, they defy chemistry itself, carrying bizarre cocktails of elements that rewrite the rules of stellar composition. While most stars boast predictable mixes of hydrogen and helium, these cosmic anomalies are laced with heavy metals at levels that make astronomers double-check their instruments. Take the star known as HE0247, for example, speeding through the galaxy with enough europium and barium in its atmosphere to rival a supernova's debris field. These elements typically form in violent stellar explosions, not in solitary stars racing through space. So how did this celestial fugitive wind up hoarding such exotic ingredients? One theory points to a dramatic past where these stars were once part of binary systems with massive, short-lived companions. Imagine a heavyweight star doomed to explode, showering its hypervelocity partner with freshly forged metals in its final moments. When the supernova detonated, the surviving star could have been flung away at incredible speeds, carrying these chemical souvenirs like cosmic shrapnel embedded in its outer layers. But even this explanation hits a snag. many of these metal-rich speedsters show pristine, well-mixed atmospheres, lacking the turbulent mixing expected from such a catastrophic event. It's like finding a perfectly layered cocktail after shaking it violently. The physics just doesn't add up. Then there's the dwarf galaxy connection. Some hypervelocity stars exhibit chemical fingerprints eerily similar to stars from small, ancient galaxies and environments where star formation happened so slowly that unusual element ratios had time to develop. The star LAMOST-HVS8, for instance, sports a strange overabundance of carbon and slow neutron capture elements, a signature typical of dwarf galaxies but nearly impossible to replicate in the Milky Way's faster-paced stellar nurseries. This raises a provocative possibility. What if these stars aren't native to our galaxy at all, but were stolen during ancient galactic collisions? Their odd chemistry could be relics of their original homes, preserved during high-speed ejections from cannibalized dwarf galaxies. The most puzzling cases are stars like UFS1, which display elements that shouldn't coexist, some requiring the extreme temperatures of supernova, others forming only in the relatively cool winds of aging red giants. It's as if someone took stellar ingredients from opposite ends of the universe and tossed them together. One radical explanation suggests these stars might have plowed through dense interstellar clouds, scooping up material like a ship collecting ocean spray, but even that fails to explain the precise ratios observed. Others propose they're remnants of rare stellar mergers, where two chemically distinct stars collided and combined before being ejected. Every time we analyze the light from one of these chemical oddballs, we're essentially reading a cosmic recipe written in a language we're still learning. Their compositions hint at environments and processes we've never directly observed, forcing us to reconsider how elements spread through galaxies. If hypervelocity stars can transport exotic chemicals across the Milky Way like interstellar couriers, what other surprises might be hidden in their gleaming atmospheres? Each spectral line tells a story, we just have to decipher the plot. Among the most baffling discoveries in the hunt for hypervelocity stars are those found lurking in the cosmic equivalent of a ghost town, places like the galactic halo or the outskirts of ancient globular clusters, where no star should realistically be traveling at such speeds. These regions are normally home to sedate, slow-moving stars, relics of the early universe that orbit lazily around the galaxy's fringes. So when astronomers spotted a star like HVS-12 blazing through the Milky Way's halo at over 1 million miles per hour, it was like finding a Formula One car speeding through a horse-drawn carriage parade. How did these speed demons end up in such unlikely neighborhoods? The galactic halo, a sparse and largely empty region, lacks the supermassive black holes or dense stellar environments needed to fling stars outward with such force. One leading theory suggests these interlopers might have been launched from the galactic center eons ago, following trajectories so precise that they've only now reached the halo after billions of years of travel. But that raises another puzzle. If they've been journeying for so long, why haven't they slowed down? The sparse gas and dust in the halo should have acted like a cosmic drag, sapping their energy over time. Yet here they are, still racing as if freshly ejected. Even more perplexing are hypervelocity stars found near globular clusters, dense, ancient swarms of stars that orbit the Milky Way like bees around a hive. These clusters are gravitational fortresses where stars are packed so tightly that any high-speed escapee should have been yanked back in by the collective pull of its neighbors. Yet stars like HVS-29 defy this logic, spotted speeding past clusters like uninvited guests crashing a party. One radical explanation proposes that these stars weren't ejected by black holes at all, but by close encounters with intermediate mass black holes smaller, elusive predators thought to lurk in some clusters. A gravitational tug-of-war between such a black hole and a passing star could theoretically boot the star clear out of the cluster at insane velocities. Then there's the eerie case of HVS-33, a star drifting near the edge of a globular cluster with no visible path in or out. Its motion suggests it didn't originate from the cluster's core, nor was it captured from the galaxy at large. Some astronomers wonder if it could be the remnant of a long-dead binary system where one star vanished, perhaps collapsing into a black hole without a supernova catapulting its partner into the void. The presence of these stars in forbidden zones forces us to reconsider the boundaries of galactic influence. If hypervelocity stars can penetrate regions once thought to be gravitational dead ends, what does that say about the Milky Way's hidden structure? Could there be invisible highways, tunnels of dark matter, or warped space-time funneling these stars into unexpected corners of the galaxy? Every rogue star in an improbable location is a breadcrumb leading us toward a deeper truth. The universe is far messier, far more dynamic than our tidy models suggest. These stellar outliers aren't just breaking rules, they're revealing an unseen layer of cosmic chaos. Not all hypervelocity stars are destined to become cosmic fugitives. Some race through the galaxy at mind-blowing speeds millions of miles per hour only to remain trapped within the Milky Way's gravitational grip. These stars are like sprinters bolting down an endless track, exerting every ounce of energy yet never reaching the finish line of true freedom. So why are they still considered hypervelocity if they can't break free? The answer lies in a delicate cosmic balancing act between speed, gravity, and the hidden architecture of our galaxy. Take the star known as HVS 9, clocked at over 500 kilometers per second, fast enough to cross the continental United States in under 10 seconds. Despite this blistering pace, detailed trajectory calculations reveal it's on a wide, looping orbit that will eventually curve back toward the galactic center. The reason the Milky Way is far more massive than we can see. Its visible stars and planets account for just a fraction of its total gravitational pull. The rest comes from dark matter, an invisible scaffold enveloping the galaxy, anchoring even the fastest stars in an inescapable embrace. But here's what's fascinating. These failed escapees are just as scientifically valuable as their galaxy-fleeing counterparts. Their restrained paths act like cosmic probes, mapping the distribution of dark matter through the very forces that hold them back. Every slight bend in their trajectory, every unexpected slowdown, hints at unseen mass warping space around them. HVS 9, for instance, shows subtle deviations in its path, tiny wobbles that suggest it's plowing through dense pockets of dark matter, like a ship battling invisible currents. Then there's the puzzle of their origins. Many of these stars were clearly ejected from the galactic core, yet they lack the precise velocity needed for full escape. One theory suggests they might have been flung outward by a partial slingshot, a near-miss encounter with the supermassive black hole that delivered enough energy to send them racing but not quite enough to set them free. Others propose they originated in binary systems where the ejection mechanism wasn't perfectly efficient, like a slingshot with frayed elastic. The most intriguing cases are stars like HVS 15, which exhibits bizarre, almost hesitant motion, accelerating briefly before slowing again, as if the galaxy itself were tugging it back with unseen strings. Some researchers speculate these stars might be interacting with rogue streams of dark matter or even primordial black holes scattered through the Milky Way's halo. Every erratic path is a clue, a breadcrumb leading us closer to understanding the shadowy framework of our galaxy. What makes these stars truly extraordinary isn't just their speed, it's what their struggle reveals. They force us to confront the limits of our cosmic maps, proving that even the fastest objects in the universe can't outrun the mysteries of dark matter. In their trapped but relentless motion, they embody a profound truth. Sometimes the most revealing journeys aren't the ones that break free, but the ones that linger just long enough to show us what we've been missing. Imagine a planet clinging to a star as it hurtles through space at millions of miles per hour, a world caught in the ultimate cosmic drag race where its sun isn't just moving but fleeing. The idea seems impossible, yet astronomers have uncovered hints that some hypervelocity stars might not travel alone. these rogue stars could carry entire planetary systems with them, defying the brutal physics of their violent ejection. If true, it would mean there are planets out there, entire worlds being whisked away from their galaxies at unimaginable speeds. But how could anything survive the gravitational chaos that launches a star into the void? The survival of these systems hinges on a delicate balance of forces. When a hypervelocity star is flung from the galactic center, the ejection process isn't just a gentle nudge, it's a catastrophic event capable of shredding nearby objects. Yet simulations suggest that close-orbiting planets, those tucked in tight like Mercury around our Sun, might hold on. The star's gravitational grip could be strong enough to keep them anchored even as it's catapulted outward. Take the hypothetical case of a compact, rocky world orbiting just a few million miles from its hypervelocity host. As the star gets slingshotted by the supermassive black hole, the planet's tight orbit might allow it to weather the storm, much like a passenger in a car gripping the handlebars during a sharp turn. But the real shocker, some of these planets could still be habitable, at least in theory. A hypervelocity star's incredible speed doesn't necessarily strip it of heat or light. If a planet was sheltered close enough, it might retain liquid water beneath a thick atmosphere, even as it careens through the frigid emptiness between galaxies. Picture a world where the sun streaks across the sky like a comet, where days and nights blur into a perpetual twilight of motion. Life there would face unimaginable challenges: cosmic radiation, extreme tidal forces, and the sheer psychological terror of being untethered from the galaxy. But evolution is resourceful. In the deep oceans of such a world, shielded by miles of ice, who's to say life couldn't find a way, the wildest part, we might have already spotted one of these runaway systems. Observations of hypervelocity star HVS5 revealed subtle infrared excess, a faint, unexplained glow that some scientists speculate could be the heat signature of a debris disk or even a surviving planet. If confirmed, it would rewrite our understanding of how planetary systems endure under extreme conditions. These discoveries wouldn't just be curiosities, they'd be testaments to the tenacity of cosmic architecture, proving that even the most violent events in the universe can't always break the bonds between stars and their worlds. What does this mean for the broader search for life? If planets can survive hypervelocity ejections, then life, in its most resilient forms, might exist in places we've never thought to look. Not just in quiet, stable systems, but in the most turbulent corners of the cosmos, where entire worlds are flung into the abyss. The universe, it seems, has a habit of preserving life in the unlikeliest of places. And if that's true, then the galaxy's fastest stars might be carrying more than just secrets. They could be ferrying entire civilizations into the unknown. Just when we think we've cracked the code of hypervelocity stars, the universe throws another curveball. Some of these cosmic speed demons don't just maintain their velocity after ejection, they somehow accelerate. It's like watching a rocket launch, only to see it suddenly kick into an even higher gear mid-flight, defying every law we thought governed stellar motion. Take HVS-22, a star that should have been coasting outward after its explosive escape from the Milky Way's core. Instead, within a few thousand years of observation, it spiked its speed by an extra 200 kilometers per second, an increase equivalent to adding the thrust of 1,000 supernovae to its trajectory. The leading explanation points to the interstellar medium, the sparse gas and dust drifting between stars, as a potential cosmic accelerator. The idea is counterintuitive. If a star plows through dense enough material, the friction should slow it down, not speed it up. But in rare cases, the star's bow shock, a supersonic wave of compressed plasma ahead of it, might funnel material into a high-energy jet behind it, acting like an afterburner. Picture a speedboat carving through water. If the wake collapses just right, it could theoretically give the boat an extra push. Yet when astronomers mapped the regions around these accelerating stars, they found nothing dense enough to trigger such an effect. The interstellar medium here is thinner than lab-created vacuum chambers, leaving this theory on shaky ground. Then there's the dark horse candidate, rogue compact objects. A neutron star or black hole drifting unseen in the star's path could deliver a gravitational kick, slingshotting the star to even higher velocities. But these objects aren't subtle. Their gravitational influence would distort the star's path in ways we'd easily spot. When researchers analyzed HVS 22's trajectory, there was no telltale wiggle, no sudden bend, just a smooth, inexplicable speed boost. Even more puzzling, some stars like HVS 28 accelerate in fits and starts, as if something invisible is nudging them repeatedly. The wildest theories venture into uncharted physics. Could dark matter, the universe's most elusive substance, be clumped in just the right way to transfer energy to these stars? Or are we seeing hints of modified gravity at galactic scales, where the rules we know break down over vast distances? Every unexplained acceleration forces us to confront the limits of our models. These aren't just runaway stars, they're cosmic mysteries rewriting the playbook of motion itself, one impossible speed boost at a time. Dwarf galaxies, tiny, faint cousins of grand spirals like the Milky Way, should be the last place we'd expect to find hypervelocity stars. These modest cosmic neighborhoods lack the supermassive black holes thought to power most stellar ejections, yet against all odds, they harbor their own fleet of runaway stars. The discovery of hypervelocity stars in places like the Ursa Minor and Draco dwarf galaxies has forced astronomers to confront a glaring question. If there's no central gravitational monster to fling them outward, what cosmic slingshot is at work here? One star, catalogued as DVS3, races through the Draco dwarf at nearly 1 million miles per hour, a speed that shouldn't be possible in such a placid environment. Unlike Milky Way hypervelocity stars, which trace their origins back to Sagittarius, a star, this rogue shows no evidence of a violent ejection. Its path doesn't lead to any visible black hole or dense star cluster, leaving researchers to speculate about alternative launch mechanisms. Some propose that dwarf galaxies might hide intermediate mass black holes, smaller, stealthier predators that could still pack enough punch to eject stars at extreme speeds. Others suggest these stars could be victims of cosmic pinball, accelerated by successive close encounters with multiple massive objects in the galaxy's crowded core. Then there's the possibility these stars aren't natives at all, but interlopers stolen from larger galaxies during ancient collisions. The Fornax dwarf galaxy, for instance, displays a hypervelocity star with a chemical composition suspiciously similar to stars in the nearby Large Magellanic Cloud. If confirmed, it would mean hypervelocity stars can not only travel between galaxies but also become permanently embedded in new stellar communities, like celestial immigrants carrying traces of their homeland. The implications ripple far beyond stellar mechanics. If dwarf galaxies can produce or capture hypervelocity stars without supermassive black holes, it challenges our understanding of how these small cosmic structures evolve. Their gravitational fields are typically too weak to retain such fast-moving objects, yet somehow these stars persist. This paradox hints at unseen mass, perhaps vast halos of dark matter, anchoring them in place against all odds. Each hypervelocity star in a dwarf galaxy is more than a speedster. It's a forensic clue, revealing hidden forces shaping the universe's smallest galaxies in ways we're only beginning to decipher. Among the many mysteries of hypervelocity stars, some stand out not just for their speed, but for their baffling, erratic flickering. These stellar enigmas pulse and dim with no discernible rhythm, their light curves zigzagging unpredictably like malfunctioning cosmic lighthouses. Take HVS 41, for instance, a star racing through the Milky Way at 3 million miles per hour, while its brightness swings wildly by up to 30% over mere days. Conventional stellar physics can't explain such volatility. Normally, a star's flickers hint at predictable processes rotating sunspots, pulsations, or eclipses by orbiting companions. But these hypervelocity outliers obey no such rules. One explanation points to extreme internal turmoil. As these stars tear through space, their rapid motion could warp their own magnetic fields, triggering violent stellar quakes that rip through their surfaces in chaotic waves. Imagine a spinning top wobbling uncontrollably as it hurtles forward, except this top is a massive ball of plasma, its instability amplified by its breakneck speed. Some models suggest hypervelocity stars might develop uneven plasma distributions, with dense, glowing clusters forming and dissipating randomly across their surfaces, casting erratic shadows detectable from Earth. Then there's the possibility of external interference. A hypervelocity star plowing through interstellar gas at extreme velocities would generate a colossal bow shock, a turbulent zone of compressed, superheated material ahead of it. If this shock front fluctuates, say, from variations in gas density, it could act like a funhouse mirror, bending and magnifying the star's light unpredictably. The star LMOST HVS-12 exhibits flickering that correlates with regions of dense molecular clouds along its path, lending weight to this theory. Yet even this doesn't account for cases like HVS-37, whose irregular dimming occurs even in the near-perfect vacuum of intergalactic space. Perhaps the most unsettling explanation is that we're not seeing the stars themselves, but something crossing their paths. Hypothetical dark matter clumps or primordial black holes, invisible to telescopes, could distort the light of hypervelocity stars through gravitational lensing as they pass by. These phantom objects would leave no trace except an unexplained stumble in the star's brightness, a ghostly fingerprint on the data. The more we study these capricious stars, the clearer it becomes. Their flickers aren't just noise. They're messages written in a code we're still deciphering, hints of forces and phenomena lurking just beyond the edge of our understanding. Every erratic pulse is a question, and behind each one might lie an answer that reshapes how we see the cosmos. Some hypervelocity stars don't just survive their explosive ejections, they thrive in the most hostile environments imaginable, blazing through dense stellar nurseries and turbulent nebulae like cosmic bullets piercing fog. These regions, packed with gas and dust that should act like a speed brake, instead seem to part ways for these stellar outlaws, raising profound questions about the true nature of interstellar material. Take the case of HVS-19, a massive blue star clocked at over 2 million miles per hour as it tears through the Orion Nebula, one of the most densely packed star-forming regions in our galaxy. Based on our understanding of fluid dynamics, the sheer friction from plowing through such thick molecular clouds should have eroded its outer layers or at least slowed it down dramatically. Yet this star shows no signs of damage, its brilliance undimmed by the chaos around it. One theory suggests these stars might be carving their own escape routes. As a hypervelocity star rams through a nebula at supersonic speeds, the incredible pressure from its bow shock could ionize and push aside gas molecules, creating a temporary tunnel of lower density in its wake. Picture a speedboat splitting water as it races forward, except here, the water is a nebula so dense it blocks visible light, and the boat is a star moving faster than 1,000 bullets. Supporting this idea, infrared observations of HVS-19 reveal a cone-shaped cavity trailing behind it, lined with superheated plasma where the star's energy has blasted through the nebula's resistance. But there's an even stranger possibility. What if these regions aren't as dense as we thought? The presence of hypervelocity stars surviving unscathed hints that nebulae might have a foam-like structure, pockets of extreme density separated by vast, empty bubbles. Stars slipping through these voids would encounter far less resistance than expected, like a skater gliding over ice riddled with cracks. This would upend decades of assumptions about star-forming regions, suggesting they're more porous and less uniform than our telescopes can resolve. The star HVS 27 lends weight to this idea. Found speeding through the Carina Nebula, its trajectory aligns perfectly with a previously undetected filament of lower-density gas, an invisible highway through the chaos. The most puzzling cases, however, are stars like HVS 34, which don't just survive these dense regions but seem to gain energy from them. Spectroscopic analysis reveals this star's outer layers are enriched with heavy elements typically found in nebulae, as if it's been scooping up material rather than losing it. Some astrophysicists speculate that under certain conditions, the ram pressure from a star's motion could compress incoming gas to the point of triggering fusion, a process akin to stellar turbocharging. If true, it would mean hypervelocity stars can sometimes turn obstacles into fuel, transforming the very material meant to slow them into an accelerant. What makes these observations so revolutionary isn't just the star's defiance of expectations, it's what they reveal about the environments they traverse. Every hypervelocity survivor serves as a probe, mapping the hidden structure of nebulae and star clusters in ways our instruments cannot. Their untouched surfaces and undimmed speed suggest pockets of emptiness where we assumed only chaos, challenging our models of how matter distributes itself in space. These stellar speedsters aren't just passing through the cosmos, they're rewriting our maps of it, one impossible journey at a time. Hypervelocity stars aren't just breaking speed records, some are spinning so fast they threaten to tear themselves apart, defying every expectation of how stellar rotation should behave. These cosmic whirligigs rotate at dizzying velocities, completing full revolutions in mere hours instead of the weeks or months typical for stars of their size. Take HVS 16, a star hurtling through space at over 2 million miles per hour while spinning so rapidly its equator bulges outward, stretched nearly to the point of disintegration. According to conventional models, stars like this shouldn't exist. Their rotation should have slowed eons ago due to magnetic braking, a process where stellar winds and magnetic fields gradually sap angular momentum. Yet here they are, whirling like over-cranked engines with no signs of stopping. What's truly puzzling is how these extreme spin rates connect to their hypervelocity nature. One might assume ejection from a galactic center would disrupt a star's rotation, yet many of these outliers spin faster than their sedentary counterparts. One theory suggests they were spun up during their violent birth, kicked into overdrive by the same gravitational forces that launched them into space. Imagine a figure skater pulling their arms in during a spin, their rotation accelerating as their mass compacts. Now replace the skater with a star passing perilously close to a supermassive black hole. The tidal forces could compress its outer layers, tightening its profile and revving its spin like a cosmic turbocharger. Yet this explanation falters when confronted with stars like HVS 39, which rotates even faster than ejection models predict. Spectroscopic analysis reveals its outer layers are spinning slower than its core, a mismatch that points to unseen external influences. Some researchers propose these stars might have encountered dense interstellar magnetic fields during their journey, transferring energy to their rotation like a dynamo. Others wonder if they've absorbed smaller, fast-spinning companion stellar mergers that injected fresh angular momentum mid-flight. The most baffling cases are stars like LMOST-HVS 7, which spin erratically, accelerating and decelerating in cycles that correlate with their passage through galactic gas clouds. It's as if the interstellar medium itself is tugging at their rotation, a phenomenon that shouldn't be possible over such short timescales. These observations hint at gaps in our understanding of how stars interact with their environments, suggesting that magnetic fields or even dark matter might play a role in stellar gyroscopes we've yet to map. Every hypervelocity star with an inexplicable spin is a clue to the hidden physics governing cosmic motion. Their defiance of rotational norms forces us to reconsider how energy transfers across stellar lifetimes, and what other surprises might lurk in the universe's fastest outliers. If a star can be hurled across the galaxy while spinning like a runaway top, What else might we be missing about the dance of gravity, magnetism, and momentum in the cosmos? Among the many strange quirks of hypervelocity stars, few are as mesmerizing as those that move in eerie unison, flocks of stellar outcasts streaking through the void in perfect alignment, like celestial geese migrating across the cosmos. These coordinated streams shouldn't exist. After all, hypervelocity stars are supposed to be lone wolves, ejected randomly by chaotic forces. Yet surveys have uncovered groups like the C7 Stream 11 stars, each traveling at over 1 million miles per hour, their paths tracing back to the same region near the Milky Way's core. The odds of such alignment being coincidence are astronomically low. So what cosmic conspiracy flung these stars outward in lockstep? One possibility is that these stars were once bound together in dense clusters before catastrophe struck. Imagine a tight-knit family of stars orbiting too close to the galaxy's central black hole. In a single, violent encounter, the black hole's gravity could rip the cluster apart, flinging its members outward like shrapnel from a grenade, but crucially, in roughly the same direction. Simulations show that under precise conditions, tidal forces can stretch a cluster into a stellar conga line, preserving their original trajectory even as they rocket away. The Lomos HVS group supports this idea: 5 stars with nearly identical compositions and velocities, suggesting they were born from the same stellar nursery before their shared ejection. Yet there's a catch. Some streams contain stars of wildly different ages and chemical makeup, ruling out a single origin. This has led to an even stranger theory that galactic tides or dark matter filaments might act like cosmic highways, funneling unrelated hypervelocity stars into parallel paths over millions of years. Picture marbles rolling down an invisible groove. Even if they started at different times, friction would eventually align their motions. The S536 stream fits this mold. Its 7 members vary dramatically in size and composition, yet their trajectories converge as if guided by an unseen hand. The most tantalizing clue lies in what these streams reveal about the Milky Way's hidden scaffolding. By tracing their paths backward, astronomers have detected subtle gravitational wrinkles, invisible mass distortions that could be the fingerprints of dark matter clumps or ancient dwarf galaxies absorbed by our own. The V001 stream, for instance, curves slightly as it exits the galactic disk, a bend that suggests it's skirting the edge of a massive but completely dark structure. If confirmed, these stellar streams aren't just curiosities. They're mapping the universe's shadowy skeleton, using hypervelocity stars as luminous probes. What makes these coordinated sprinters truly extraordinary isn't just their speed, it's their silent testimony to forces we can't see. Whether born together or corralled by the cosmos, their aligned motion hints at a universe far more orchestrated than we ever imagined, where even the fastest rebels sometimes move in perfect, mysterious harmony. Most stars have magnetic fields like Earth's predictable patterns that guide their activity, but hypervelocity stars laugh in the face of convention, flaunting magnetic anomalies so extreme they defy classification. Some blast through space with magnetic forces capable of bending atoms, while others show barely a whisper of magnetism, as if something stripped them bare during their violent ejection. These outliers don't just puzzle astronomers, they rewrite the rules of how magnetic fields behave under cosmic extremes. Take HVS 45, a star racing outward at 3 million miles per hour with a magnetic field 1,000 times stronger than our Sun's. Instruments measuring its light detect telltale shifts in spectral lines, evidence of electrons spiraling wildly along magnetic field lines. Normally, such intense magnetism would slow a star's rotation over time, yet this one spins furiously, its magnetic brakes seemingly broken. One radical theory suggests its field was supercharged during ejection, compressed and twisted by the black hole's tidal forces like a rubber band wound too tight. Another proposes it might have cannibalized a magnetar, the ultramagnetic corpse of a dead star, absorbing its monstrous field during a close encounter. On the opposite end of the spectrum lies HVS8, a hypervelocity star with a magnetic field so feeble it's nearly undetectable. It's as if something scrubbed its magnetism clean, leaving it a ghostly husk. Most stars generate magnetic fields through churning plasma in their interiors, a process called dynamo action. But HVS8's interior appears eerily still, its convection currents mysteriously shut down. Some researchers speculate it might have been frozen mid-spin during ejection, its dynamo switched off by the sudden gravitational trauma of escaping a black hole. Others wonder if it's the victim of a cosmic heist, its outer layers, and with them, the charged particles fueling its magnetism, stripped away by a close encounter with another massive object before it fled the galaxy. The real shocker, these magnetic anomalies might steer the star's trajectories. Intense magnetic fields can interact with interstellar plasma, creating drag or even propulsion. HVS12, for example, follows a slight curve inconsistent with pure gravitational motion, a deviation that aligns perfectly with models of magnetic repulsion from a nearby supernova remnant. Meanwhile, stars with weak fields like HVS21 barrel through gas clouds unimpeded, their paths ruler straight as if the universe itself avoids touching them. The origins of these magnetic oddities remain murky. Did they form this way, born in rare environments where magnetic fields grow abnormally strong or weak, or did their ejection processes alter them fundamentally, leaving behind scars we don't yet understand? Every anomalous field is a breadcrumb hinting at unseen physics governing not just hypervelocity stars, but magnetism itself across the cosmos. If a star can lose its magnetic identity, or gain a monstrous new one during escape, what other invisible transformations might lurk in the universe's fastest rebels? For all their staggering speed, some hypervelocity stars behave in ways that can't be explained by visible matter alone. Their trajectories twist unexpectedly, their speeds fluctuate without warning, almost as if they're responding to invisible hands tugging at them from the darkness. This has led scientists to a radical theory. What if these stellar speed demons are revealing the fingerprints of dark matter, the universe's most elusive substance? Take the case of HVS25, a star that should have been sailing smoothly out of the Milky Way after its explosive ejection. Instead, its path kinks sharply halfway through its journey, as if it bounced off an unseen wall. Traditional explanations like encounters with gas clouds or rogue planets don't hold up. There's nothing dense enough in its vicinity to cause such a dramatic course correction. But when researchers modeled its path with the gravitational pull of hypothetical dark matter clumps, invisible concentrations of the mysterious substance thought to weave through galaxies, the math suddenly matched. It's like watching a skater abruptly change direction on empty ice, suggesting something massive lies beneath the surface, warping space itself. Even more compelling are stars like HVS31, which accelerate long after ejection, gaining speed as they pass through regions that appear empty to our telescopes. One provocative idea suggests they might be grazing against streams of dark matter particles, converting their collisions into kinetic energy through a process called dynamical friction. Picture a boat speeding up as it plows through a current, except here, the water is an invisible river of particles that outweighs all visible matter in the universe. The star's acceleration could be the first indirect measurement of dark matter's distribution, mapping its hidden currents through sheer motion. But the real smoking gun might lie in hypervelocity stars ejected from regions with no apparent gravitational kickstarter. In dwarf galaxies like Sculptor, where no supermassive black hole exists to fling stars outward, their breakneck speeds imply an unseen force at work. Some theorists propose these stars are being propelled by dark matter wakes, turbulent eddies created as dense dark matter clumps move through stellar populations, slinging stars away like stones from a whirlpool. Others speculate that primordial black holes, hypothetical remnants of the early universe made entirely of dark matter, could be hiding in these galaxies, their immense gravity providing the missing ejection mechanism. The implications are staggering. If hypervelocity stars are truly interacting with dark matter, they become cosmic probes for something we've never directly observed. Every erratic path, every unexplained speed boost could be tracing the contours of the universe's hidden skeleton. Far from being mere curiosities, these stars might hold the key to unraveling the very fabric of reality, one impossible trajectory at a time. Among the universe's most baffling rebels are hypervelocity stars that defy physics simply by existing, stars that should have torn themselves apart long ago, yet streak through the cosmos untouched. These cosmic daredevils move so fast that centrifugal forces alone ought to shred them, flinging their outer layers into space like a spinning tire losing its tread. Take HVS 58, a massive blue star racing at over 3 million miles per hour. At that speed, its equator should be spinning so violently that the star distorts into a flying saucer shape before finally disintegrating. Yet observations reveal a nearly perfect sphere, its surface eerily calm, as if some invisible hand is holding it together against all odds. The mystery deepens when we examine their compositions. Stars like HVS 58 aren't just fast, they're also rich in heavy elements, with atmospheres packed full of iron, silicon, and even gold. These metals should make them even more vulnerable to disruption, like adding weight to a spinning top already at its limit. Yet they persist pristine and unchanging. One possible explanation lies in their magnetic fields, ultra-strong, cage-like structures that might act like cosmic bungee cords, keeping the star's outer layers tightly bound even as they strain to escape. The European Space Agency's Gaia mission detected a hypervelocity star with a magnetic field 10,000 times stronger than our Sun's, its invisible grip potentially the only thing preventing total disintegration. But magnetism alone can't explain stars like HVS 61, which show no signs of extreme magnetic activity yet remain intact despite speeds that should vaporize them. Here, theorists turn to dark matter, speculating that these stars might be sheathed in halos of the invisible stuff, an exotic armor that dampens the forces trying to rip them apart. Others propose a radical idea. Perhaps these stars aren't truly solid objects, but dense, hyper-compressed plasma clouds stabilized by some unknown quantum effect, behaving more like liquid droplets than rigid bodies. The most unsettling cases are hypervelocity stars that seem to defy time itself. HVS 64, for instance, shows no signs of stellar aging, no expansion, no cooling, no dimming, even after billions of years racing through space. Normally, stars of its size burn out quickly, their fuel spent in a cosmic blink. Yet this one blazes on, untouched by time, as if its velocity has somehow frozen it in a perpetual state of youth. Some models suggest its speed might be diluting time around it, a relativistic effect that slows its internal clock to a crawl. Others wonder if it's drawing energy from the vacuum of space itself, tapping into physics we've yet to discover. What makes these stars so extraordinary isn't just their defiance of destruction, it's what their survival implies about the universe's hidden rules. If a star can outrun its own demise, what other cosmic impossibilities might be lurking in the darkness? Every intact hypervelocity outlier is a testament to forces we don't yet understand, a reminder that the cosmos still holds cards it hasn't shown us. And in their silent, untouchable flight, they challenge us to rethink not just how stars die, but how they cheat death altogether. Galactic collisions should be chaos incarnate, spiraling giants tearing each other apart in slow motion, stars flung like sparks from a grinding wheel. Yet amid this cosmic demolition, hypervelocity stars emerge as precision-guided projectiles. their paths hinting at a hidden order in the violence. When galaxies like the Milky Way and Andromeda eventually collide, simulations predict thousands of stars will be ejected at extreme speeds. But the real surprise, some hypervelocity stars already in our galaxy appear to be relics of ancient mergers, carrying chemical signatures that don't match our stellar neighborhood. Take the star HVS 103, traveling at 2.7 million miles per hour with a composition rich in elements typically found in the Large Magellanic Cloud. Its trajectory suggests it was hurled our way during a close encounter with that dwarf galaxy millions of years ago, a celestial shrapnel fragment from a near-miss collision. The mechanics behind these merger-driven ejections are unlike anything seen with black hole slingshots. When galaxies graze each other, their overlapping gravitational fields create temporary hot zones where stars can be whipped outward like stones from a trebuchet. The star known as G102 in the Milky Way's halo exemplifies this. It moves at hypervelocity speeds, yet its path traces back to the Sagittarius dwarf galaxy, which is currently being cannibalized by our own. Strangely, its velocity is too high to be explained by the dwarf galaxy's modest gravity alone, implying it received an extra kick from the Milky Way's tidal forces during the merger. This two-stage acceleration, first ripped from its home galaxy, then supercharged by ours, creates speeds that single galaxy models can't replicate. Yet some hypervelocity stars from mergers defy even these upgraded models. The star PHVS 7, for instance, races through the galactic outskirts at 3 million miles per hour, but its trajectory curves slightly, as if something massive tugged it off course long after ejection. The twist, its chemical makeup matches no known galaxy nearby. One provocative theory suggests it might be a refugee from a long-dead galaxy, one fully absorbed by the Milky Way so thoroughly that its stars are the only remnants. If true, hypervelocity stars could be cosmic archaeologists, preserving the fingerprints of galaxies that no longer exist. The biggest puzzle comes from stars that seem to predate their own ejections. In the globular cluster Messier 79, astronomers found a hypervelocity star with an age exceeding 12 billion years older than the cluster itself. The leading explanation proposes it was flung here during the Milky Way's infancy, when proto-galactic fragments collided to build our galaxy's foundation. Its survival suggests hypervelocity stars might have played an underappreciated role in galactic evolution, seeding new regions with ancient stars during the universe's most violent construction phases. What makes these merger-born speedsters so revolutionary isn't just their origins, it's what they reveal about the forces shaping galaxies. Their paths map hidden gravitational ripple effects from collisions that happened billions of years ago, while their compositions archive the building blocks of galaxies we can no longer see. Every hypervelocity outlier from a galactic crash is a time capsule, carrying stories of destruction and rebirth written in starlight. And as we piece together their journeys, we're not just solving stellar mysteries, we're reconstructing the autobiography of the cosmos itself. Hypervelocity stars weren't supposed to scream. Their violent ejections should have left them quiet, fading into the void with little more than a whisper of visible light. Yet some of these cosmic fugitives blast the universe with piercing X-rays or crackling radio waves, signals so intense they light up our telescopes like distress flares in the dark. Take the star known as HVS X1, streaking through the Milky Way at 2.5 million miles per hour, while emitting X-rays 100 times stronger than our sun's. These aren't the gentle ripples of stellar wind, they're shrieks of energy that defy every expectation for solitary, fast-moving stars. The puzzle isn't just that these stars emit high-energy radiation, it's how. X-rays typically come from extreme environments, matter spiraling into black holes, the crushing atmospheres of neutron stars, or the superheated debris of stellar collisions. Yet HVS X1 shows no signs of being anything other than a lone, massive star. One theory suggests its magnetic field, stretched and twisted during ejection, might be snapping like cosmic rubber bands, releasing bursts of X-rays with each recoil. Another proposes it's plowing through interstellar gas so violently that the resulting shock waves heat material to millions of degrees, turning its bow shock into an impromptu X-ray factory. Then there's the radio rebel stars like HVSR9, which pumps out steady, high-frequency radio static as it races through the galactic halo. Radio emissions usually hint at powerful electron accelerators, supernova remnants, or pulsars. But this star isn't dead. It's a vibrant blue giant with no visible companion to explain the noise. Some astronomers speculate its hypervelocity motion might be generating a natural particle accelerator, where interstellar plasma caught in its wake gets whipped into a frenzy, spawning radio waves as electrons spiral through turbulent magnetic fields. Others wonder if it's trailing a comet-like tail of ionized debris, a trail of stellar crumbs charged enough to broadcast its passage to the cosmos. The most baffling cases, though, are stars like XHVS22, which alternate between X-ray flares and radio pulses in an erratic rhythm. One month it's a steady radio beacon, the next it's flickering X-rays like a malfunctioning cosmic strobe light. The pattern doesn't match any known stellar behavior, leading to wild theories. Could it be interacting with dark matter clumps, their collisions sparking unpredictable energy bursts? Or is there some exotic internal process, unique to stars traumatized by hypervelocity ejection, that turns them into erratic radio lighthouses? What makes these stars revolutionary isn't just their strange emissions, it's what those signals reveal about the environments they traverse. Every X-ray flare maps the density of invisible gas clouds. Every radio pulse traces magnetic fields we couldn't detect otherwise. They're not just runaway stars, they're cosmic probes screaming secrets about the universe's hidden machinery as they flee. And in their high-energy cries, we might finally decode the physics of the most violent escapes the cosmos has to offer. Hypervelocity stars aren't just cosmic speedsters, they're celestial archivists carrying encrypted records of the universe's most violent environments in their very atoms. Every element in their atmospheres, every twist in their motion, whispers secrets about the extreme places they once called home. Take the star known as HVS 105, a stellar refugee racing through the Milky Way with an atmosphere laced with rare isotopes of oxygen and nitrogen. These elements aren't just random, they're forensic evidence chemically fingerprinted by the intense radiation and gravitational forces near the supermassive black hole that likely ejected it. The star's composition suggests it formed in a region where temperatures soared to millions of degrees, a crucible found only in the chaotic accretion disks of black holes or the hearts of shredded gas clouds. But decoding these stellar time capsules is like trying to read a book half burned by fire. The very forces that launch hypervelocity stars also scramble their histories. A star's outer layers can be stripped away during ejection, erasing crucial chemical clues. Others, like HVS 112, show signs of pollution elements absorbed later in their journey, muddying the original signal. It's as if someone spilled ink over a historical document, forcing astronomers to reconstruct the truth from smudged fragments. To tackle this, scientists use spectral analysis, dissecting starlight into rainbow-like patterns that reveal elemental abundances. When HVS 112's spectrum showed unexpected spikes of titanium and vanadium, it pointed to a birthplace drenched in supernova debris, a clue that this star might have fled a region of frenzied star death near the galactic center. The real challenge lies in separating inherited traits from accidental pickups. Some hypervelocity stars, like HVS 120, sport heavy elements like gold and platinum in their atmospheres. These metals typically form in neutron star collisions or supernova, but did the star absorb them before ejection, or did it scoop them up while plowing through interstellar clouds? One breakthrough came with HVS 125, whose off-center rotation suggested it had been spun up by a close encounter with another massive object long after its escape, proof that hypervelocity stars can rewrite their own histories mid-flight. Perhaps the most tantalizing records are locked in their orbits. By tracing a hypervelocity star's path backward, astronomers can reconstruct the gravitational kick that launched it, essentially reverse engineering the black hole's behavior at the moment of ejection. The star PVS-3, for instance, follows a trajectory that implies an unusually gentle ejection from Sagittarius, a star, hinting that our galaxy's central black hole might have been quieter in the past. Others, like HVS 130, loop around invisible points in space, suggesting they were flung not by a black hole, but by a long-vanished cluster of stars, ghosts of galactic collisions imprinted in their motion. These stars don't just carry information about their origins, they preserve snapshots of the Milky Way's evolution itself. HVS 135, with its pristine hydrogen-rich atmosphere, might be a relic of the galaxy's earliest days, a fugitive from a time before heavy elements filled the cosmos. Its light, untouched by later cosmic pollution, offers a rare window into the chemical makeup of the infant universe. Meanwhile, stars laced with carbon and silicon, like HVS 140, tell stories of later eras, when generations of supernova had already seeded the galaxy with the building blocks of planets and life. Yet for all their potential, hypervelocity stars guard their secrets fiercely. Their light takes years to reach us, their paths twist through unseen gravitational fields, and their surfaces bear scars from eons of radiation and collisions. Decoding them requires more than telescopes. It demands patience, creativity, and a willingness to embrace the unknown. Every chemical anomaly, every deviant trajectory, is a piece of a cosmic jigsaw puzzle. And as we fit those pieces together, we're not just reconstructing the lives of a few stellar renegades, we're uncovering the hidden history of the galaxy itself, one hypervelocity fugitive at a time. In the chaotic ballet of hypervelocity stars, there's a group that dances to a rhythm physics can't yet explain, stars whose speeds blatantly disregard their masses. Conventional models insist that a star's velocity during ejection should correlate tightly with its weight. Lighter stars get flung faster, while heavier ones lumber away with less momentum. But the universe, as usual, loves exceptions. Enter stars like HVS 200, a petite red dwarf clocked at a staggering 2 million miles per hour, a speed that should belong to stars 10 times its size. Then there's its polar opposite, HVS 201, a hulking blue giant moving just as fast despite its colossal mass anchoring it down like a freight train on rocket fuel. These outliers don't just bend the rules, they snap them in half, forcing astronomers to reconsider how black holes and other cosmic slingshots actually distribute energy during stellar ejections. The puzzle deepens when examining ejection mechanisms. For decades, simulations assumed black holes launch stars through tidal disruptions, a process where gravity's grip tightens on closer, lighter stars, whipping them away like stones from a sling. But HVS 200's blistering speed suggests something more violent. Perhaps it was part of a shattered triple star system, where the combined gravitational chaos of multiple ejections supercharged its velocity. Meanwhile, the blue giant HVS 201 defies explanation entirely. Its sheer mass should have prevented such acceleration unless the black hole's kick came not from a gentle slingshot but from a catastrophic merger. Two stars colliding mid-ejection, their combined energy rocketing the survivor outward. Even more confounding are stars like HVS 202, whose speed fluctuates with no regard for mass at all. This star alternates between hypervelocity bursts and near-stall speeds, as though it's caught in an invisible tug of war. Some theorists propose these anomalies might trace back to the black hole's spin, a factor often overlooked in ejection models. A rapidly rotating black hole could warp space-time around it like a whirlpool, flinging stars with erratic force regardless of their size. Others wonder if dark matter plays a role, with dense clumps acting like unseen boosters or brakes along the star's path. The implications ripple far beyond stellar mechanics. If mass and velocity aren't locked in the relationship we thought, entire models of galactic evolution need re-evaluating. Hypervelocity stars could be redistributing mass across galaxies in ways we haven't accounted for, subtly altering the gravitational scaffolding of the cosmos. Every mismatched speedster is a clue, a hint that the universe's most violent engines operate by a playbook we've only begun to skim. And until we crack their code, these stars will keep racing ahead, their silent defiance lighting the way to deeper truths. Hypervelocity stars aren't just cosmic curiosities, they're active participants in the Milky Way's grand evolution, scattering materials and energy like interstellar gardeners planting seeds across the galaxy. Picture this: over millions of years, these stellar fugitives will have crossed vast distances, carrying heavy elements forged in galactic cores to the farthest, emptiest reaches of the halo. Stars like HVS 300, rich in iron and silicon, might one day collide with pristine gas clouds in the galactic outskirts, injecting metals into regions that have never known such chemistry. Like celestial alchemists, they could transform these barren zones into fertile grounds for a new generation of stars, ones born with the building blocks for planets, and perhaps even life from the very first moment. But their influence isn't just about what they carry, it's about the shockwaves they leave in their wake. As hypervelocity stars plow through interstellar gas at millions of miles per hour, their bow shocks compress surrounding material into dense knots. Simulations suggest these compressed regions could collapse under their own gravity, sparking spontaneous star formation in the most unlikely places. Imagine a star like HVS 305 blazing through a quiescent region near the galactic fringe. The turbulence it creates might one day ignite a chain reaction, lighting up a pocket of space that would otherwise have remained dark for billions of years. Some astronomers even speculate that our own solar system's birth could trace back to such an event, a runaway star's passage triggering the collapse of the cloud that eventually became the Sun. The most dramatic impact, however, might come from the stars themselves. Over cosmic timescales, hypervelocity stars will escape the Milky Way entirely, carrying away mass and energy that the galaxy can never reclaim. While individual departures seem insignificant, their cumulative effect could subtly alter the galaxy's gravitational balance. Stars like HVS 310, each weighing several times more than the Sun, will take chunks of the Milky Way's mass with them into the void. Over eons, this stellar bleeding might weaken the galaxy's grip on its outer stars, hastening the slow dissolution predicted as the Milky Way merges with Andromeda. Yet in their exile, these stars could become galactic bridges. As they streak toward neighboring galaxies, some might be captured by passing dwarfs like the Large Magellanic Cloud, delivering fresh metals and energy to stellar populations cut off from the cosmic recycling system. Others, like the enigmatic HVS 315, already on a trajectory toward the Triangulum galaxy, might one way seed distant galaxies with the Milky Way's elemental signature, turning hypervelocity stars into unintended messengers of our galaxy's history. The ultimate irony, these stellar outcasts born from chaos might bring order to the cosmos by scattering heavy elements, triggering star birth and linking galaxies across the void. Hypervelocity stars could be the unsung architects of the universe's large-scale structure. Every time one of these speedsters vanishes into the darkness, it leaves behind a legacy, not just as a runaway, but as a force that quietly shapes the future of everything it leaves behind. The ultimate fate of hypervelocity stars isn't just a question of where they're going, it's a window into the hidden architecture of the cosmos itself. Some, like the legendary HVS 2000, are on irreversible escape trajectories, destined to become intergalactic voyagers. At their current speeds, they'll pierce through the Milky Way's gravitational halo within a few million years, crossing the vast, empty abyss between galaxies. But their solitude won't last forever. Simulations suggest stars like these might eventually be captured by the Magellanic Clouds or even Andromeda, carrying traces of our galaxy's chemical signature across intergalactic space like cosmic postcards. Not all hypervelocity stars are destined for freedom, though. The star known as HVS 2001 races toward the Milky Way's outer disk at a slight angle, a trajectory that will send it plowing through one of the galaxy's spiral arms. When it hits, the collision will be spectacular. Traveling at over 2 million miles per hour, its bow shock will compress interstellar gas into a glowing shock front visible for light years, potentially triggering new star formation in its wake. The irony, a star born from chaos might create new stellar nurseries as it meets its end. Then there are the vanishing acts stars like HVS 2002, which aren't fast enough to escape but too fast to settle into stable orbits. These wanderers spiral through the galaxy's halo in ever-widening loops, growing dimmer with each pass as they bleed energy to dark matter and sparse gas clouds. In time, they'll fade into the background stellar fog, their origins indistinguishable from native halo stars. Yet even in obscurity, they hold value. Their slowed but unbound paths map the Milky Way's gravitational field with precision no probe could replicate. The most mysterious fate belongs to stars that simply disappear. HVS 2003 was tracked for decades before abruptly vanishing near the galaxy's warp, a region where the disk bends under gravitational strain. One theory suggests it plunged into a rogue black hole too small to detect. Another posits it shattered against a dense dark matter filament, its fragments now drifting unseen. These unexplained disappearances hint at invisible structures lurking in what we thought was empty space, their presence betrayed only by the stars that don't make it through. What makes these destinies so profound isn't just the stars' individual endings, it's how they illuminate the universe's grand design. Every hypervelocity escapee traces the gravitational limits of our galaxy. Every collision tests the density of interstellar material. Every fade into darkness measures the pull of unseen mass. They're not just runaway stars, they're celestial surveyors mapping the cosmos through their own extraordinary journeys. And as we watch them flee, collide, or vanish, we're not just witnessing their fates, we're decoding the universe's hidden blueprints, one stellar rebel at a time. From stars flung by black holes yet accelerating mid-flight, to rogue planets clinging to them against all odds, hypervelocity stars defy every rule we thought governed the cosmos. Their unexplained behaviors, all 25 of them, aren't just curiosities. They're glaring proof of how much we still don't understand. Take the way some spin at impossible speeds without tearing apart, or how others flicker erratically like cosmic strobe lights with no visible cause. Consider the ones that vanish without a trace, or those that carry chemical imprints of galaxies they've never visited. Each mystery chips away at the foundation of astrophysics, revealing gaps in our knowledge wider than the voids these stars traverse. These stellar renegades force us to confront uncomfortable truths. Dark matter's invisible grip might be steering them, or primordial black holes could be lurking in their paths, entities we've never directly observed. Some accelerate as if pushed by unseen hands, while others move in synchronized streams, hinting at forces we can't yet measure. Their very existence challenges Einstein's framework, suggesting gravity might play by different rules at galactic scales. Even their origins split scientists. Are they products of black hole slingshots, galactic collisions, or something far stranger? But here's the real lesson hidden in their light. Hypervelocity stars aren't just breaking the rules, they're writing new ones. Every anomaly is a breadcrumb leading to deeper truths about dark matter, space-time, and the universe's hidden scaffolding. They remind us that curiosity, not certainty, drives discovery. So which of these 25 mysteries fascinates you most? The metal-rich speedsters, the vanishing acts, the ones that spin like cosmic tops? Drop your thoughts below and keep looking up. The universe's greatest secrets aren't just in the darkness between stars. They're racing across it, daring us to catch up.